We present a new method for the fast computation of contact configurations for arbitrary creatures in constrained environments. We consider the issue of computing limb configurations that are in contact with the environment. This allows virtual creatures to achieve complex tasks such as getting up from a sofa. To obtain a natural posture, we must find a good location for the end effector, but also a good configuration for the limb. But what is a good configuration? We address this question with a measure called the force transmission ratio. It is based on the manipulability ellipsoid. The length of the ellipsoid axis is proportional to the potential force that can be exerted in their direction. In this example, the configuration on the left is compatible with a horizontal force task, and the configuration on the right is compatible with a vertical task. We combine this measure with a random sampling approach independent from the environment. To do so, we select a limb and combine a number n of random postures in the reachable workspace. We repeat this process for all the limbs composing our virtual creature. At runtime, given a motion task such as getting up from a sofa, we combine the local environment with the result of the sampling that we performed offline. We then select the collision-free postures in contact with the environment, and from those, we select the best configuration according to the heuristic we introduced before. Please refer to the paper for more details. In this example, given a task represented by the black arrow, we compute appropriate limb configurations for this six-limbed insect. We compare our method with the basic closest distance approach, which is used in previous works. We can see that we obtain better results to either push a cupboard or to get up from a sofa. Here is an example of a resulting motion synthesis computed in real time with an inverse kinematic solver. We now consider motion on a climbing wall. Our method will compute appropriate configurations adapted to the motion task. On the other hand, a method such as the closest distance heuristic doesn't account for the motion task. Therefore, it will always compute the same configuration. Small variations on the environment can produce interesting results with our method. In this example, the chair on the right side is shorter than the chair on the left side, allowing the virtual human to put its arm on it. Here, given the task of pulling the cupboard, the virtual human uses the pink wall to maximize the force exerted by its foot. In this interactive scenario, a virtual human is driven by a user with a joystick. Along the trajectory, we use our method to compute the contact configurations with real-time performances. The motion is computed using a simple inverse kinematic solver that is to be replaced with a dynamic approach in future work. Here we compare again our method with the closest distance heuristic.